We can use spectrum view on the 4, 5, and 6 series oscilloscopes as a spectrum analyzer to look for steady state and transient RF activity, and then correlate that transient RF activity to other events on a circuit board. So for example, if we take a near-field probe and probe around on a circuit board, we can look for emissions in certain areas. For example, if I move the probe over to this area here, we can see on the spectrum display a broadband set of RF activity, and that's due to the fact that this is the switching power supply area of the board. There's an interesting signal that we want to look at right in this area here, right near the FPGA, where if we look at the spectral activity, we can see a signal right around 137 megahertz that is bursting high and low. That could be a real trouble spot when you go to do EMI compliance. If it's only bursting high for short periods of time, it may pass testing when you're characterizing in the lab, but as luck would have it, it would likely fail when you go and do your full compliance testing. So let's take a look at how to correlate that transient RF burst to an event on the board. Now, in order to view the time domain nature of this transient RF signal that we see here, it may be helpful to bring up the display of the time domain waveform that's being used to compute the spectrum here. And I like having the spectrum on top, so we'll just rearrange that this way. And it also may be helpful to bring up the RF magnitude versus time trace, which is giving me a measure of the total power within this 200 megahertz span. Now let's capture a little more data over time. And then it may be helpful also to enable a trigger, but let's trigger on the RF magnitude versus time. So I'm going to set the source to trigger 2, magnitude versus time, and we can adjust our trigger level to trigger just on this RF peak that we see. And we'll pause the instrument for a moment here. Now what we can see on this display is a spectrum measurement that's being made at this location in time. Now we're suspecting that this burst that we see here and in the RF power versus time, and then over here and down here as well, is showing up in the spectrum at this 137 megahertz. We can verify that by moving the spectrum time and seeing that we have that burst, that signal appearing there at about minus 40 dBm at this location in time. If I move off that, that peak goes down. If we bring that spectrum time all the way over to this next burst, we see it pop up again. So now we certainly know that this burst that we see in the time domain and in the magnitude versus time is indeed this signal at 137 megahertz. We also can see how long it's lasting. It's in the neighborhood of about 10 microseconds long. And we can also see its repetition interval. And those two pieces of information alone might give the designer enough information to know where that signal is coming from. But if not, what we can do is use the fact that we're triggering on this signal. So all we need to do is, say, add another channel with a scope probe, start probing around on the board looking for a signal that's coincident to that particular RF event. So if I probe this signal right here on the board, we can see that that signal certainly is not coincident to the RF event that we see. But if I probe this signal right here, we can see that this signal is indeed exactly coincident to that RF event. So now we've found the signal that is coincident to this particular RF emission, and that gives us an idea of where to go look on the board to help correct that. So this short video has shown how you can use spectrum view on the 4, 5, and 6 series oscilloscopes, along with the new RF versus time triggering capability to isolate transient RF events and help you to identify those electrical signals on the board that may be coincident to and may be responsible for those particular RF emissions.